Welcome back to the second part of part one notes, and that is we'll talk about differentiability and continuity. Differentiability implies continuity, meaning in order for a function to be differentiable, meaning you can take the derivative at a value, then the function is continuous at that value. However, if it's continuous, it doesn't mean it's differentiable, so it doesn't mean the same thing vice versa. So what that means is just because a function is continuous at a x coordinate, it doesn't automatically mean that the function is differentiable. And if a function is not continuous at that point, then the function is not differentiable. So if it's not continuous, you know it's not differentiable. However, if it's continuous, you still don't know if it's differentiable. But if it's differentiable, you do know it's continuous. So let's do some examples. So f of x equals the absolute value of x plus 3. So for part A, let's make the piecewise function. So the piecewise function here would be x plus 3 if x is greater than or equal to negative 3, and negative x minus 3 if x is less than negative 3. So if you look at that, to answer that question, yes, it is continuous. So that means it could be differentiable. But let's find the derivative. So if we find the derivative of the parts, right, the derivative of each part, well, remember, derivative is slope. So I don't have to do that big, long limit thing if it's a line here, because what is the slope of x plus 3? Well, the slope is 1, right? So the slope is 1 if x is greater than negative 3, right? Because remember, absolute value are pointed, so the slope at negative 3 is going to be undefined, because remember, I can't have a sharp turn. I have to have a smooth curve in order to find the slope there. So it's 1 if it's greater than negative 3, and it's negative 1 here if it's less than negative 3, right? Because we're talking about the slope. So now, finding f of negative 3, well, f of negative 3, remember, f prime of negative 3, it is undefined. It does not exist, right? Because that would be a sharp turn, and we can't find the slope at a sharp turn. Because if we go back to page 3 of our notes, remember, this implies no sharp turns, because remember, the derivative from the left would have to equal the derivative from the right in order to have it differentiable at 3 and to have a slope at 3. And notice it is not from the left and the right, the derivatives are different. So for part D, it says explain what is happening graphically. Graphically, there's a sharp turn. So that's why the derivative does not exist there. All right, so let's look at the next one. The next one is a piece function. So it might help if you draw it graphically, just to kind of get an idea. So there's kind of a rough sketch of what's happening. So notice, what is the slope for each piece? The slope would be 0, right? Because it's a horizontal line for each piece. Part B, is the function continuous at x equals 1? It is not continuous. And part C, find f prime of x and f prime of 1. Well, f prime of x, the slope of the function is 0 for all integers, and f prime of 1, well, at 1, notice it is not going to exist because you would have a vertical tangent line. And also, notice because it is not also continuous. I mean, it is continuous. It is not continuous, sorry. So therefore, it's not going to be differentiable. But also notice you'd have a vertical tangent line. So that would make it not differentiable as well. All right, example 3. If you have the square root function, so notice here the limit as x approaches 0. To find f prime of 0, we'll use the alternative derivative, alternative form. So it's equal to f of x minus f of 0, which in this case is 0, over x minus 0. So it's equal to the limit as x approaches 0 of the square root of x over x, which is equal to, when you take the square root of x and multiply it by both sides, it's the limit of x approaches 0 of x over x rad x, which is the same as the limit as x approaches 0 of 1 over rad x, which is 1 over 0, which is infinite or undefined, which means it does not exist because you have unbounded behavior. So graphically, you have the square root function, right? And notice what kind of tangent line would you have? You would have a vertical tangent line. So that's what happens graphically. That's why the derivative does not exist at 0. All right, so if you look at the bottom here, summary, to be differentiable at a point, if the derivative exists, and for that to happen, it must be continuous. The derivative on the left will have to equal the derivative on the right, and the tangent line is not vertical. So those 3 things have to happen. So to show, first of all, we have to determine if f of x is continuous or not. Or we have to, determine where f of x is not continuous or not differentiable. So remember, we're looking at the changing points. So there's 3 changing points. X equals -1. Well, f of -1, we notice, is undefined because it never equals -1. So therefore, f is not continuous because in order to be continuous, it must be defined. And therefore, it is not differentiable. At -1. So if it's not continuous at a certain point, then you know it's not differentiable. So next changing point will go to 0. Well, f of 0 is equal to 2. The limit as x approaches 0 from the left, and from the left is right here, so it's 0 squared, it's x squared plus x, which means it's equal to 0. The limit as x approaches 0 from the right would be x plus 2, which is equal to 2. So therefore, the limit as x approaches 0 of the function does not exist. Remember, because limit from the left does not equal limit from the right. So therefore, f is not continuous and not differentiable at x equals 0. So then the last point is 2. That's the last changing point. Well, f of 2 is equal to 4. The limit as x approaches 2 from the left, and the left is going to be x plus 2, so that's also going to be 4. And the limit as x approaches 2 from the right, which is x squared, is 4. So that means the limit as x approaches 2 of the function is 4. So therefore, f is continuous at x equals 2. Now we have to figure out if it's differentiable. And to find out if it's differentiable, well, a couple things. Number one, we have to find the derivative from the left and the right. Well, f prime of 2 from the left, well, notice the slope here of this line is 1. F prime of 2 from the right, well, now we have a quadratic, right? So we could find the limit as x approaches 2 of x squared minus 4, because 4 is what happens over x minus 2. So the limit as x approaches 2, and this is x plus 2, x minus 2. So when you cancel, it becomes x plus 2, which means it's 4. So the derivative from the right is 4. So therefore, f is not differentiable at x equals 2 because the derivative from the left and the right are not the same. What could happen in number 2? Draw several sketches of f of x such as f prime of 2 is 0. So if you have a function at 2, like a parabola, right, that could give you a horizontal tangent line. I'll do one more. Let's say you had a function like this, where this is 2, 0. That would be a horizontal tangent line as well. All right, so that's what happens there. Let me go back to number 1 for a second, because the last part says state the intervals of continuity and differentiability. So f is continuous on the interval of -∞ to -1, union -1 to 0, union 0 to infinity, because it is continuous at 2. However, it's differentiable from -∞ to -1, -1 to 0, 0 to 2, and then 2 to infinity, because it's not differentiable at 2, but it is continuous. All right, so next, using the provided graph, it wants us to do some things. So first of all, it wants to state where f of x is undefined. Well, in part A, f of x is not defined at C. Then it wants to say, where is f of x not continuous? Well, f is not continuous at C and F, because notice C and F is not continuous. Part C, where is it not differentiable? Well, it's not differentiable at C. It's also not differentiable at F because it's not continuous there. It's not differentiable at G because notice you have a sharp turn. You would have a vertical tangent line. And it's also not differentiable at N. You also have another sharp turn. So for part D, it says state the interval of continuity. Well, the interval of continuity would be from negative infinity to C, from C to F, from F all the way to infinity. Then it says for part E, state the intervals of differentiability. So F is differentiable from negative infinity to C, union C to F, union F to G, union G to N, and then union N to infinity. And last but not least, for part F, are D and E equivalent? And the answer is no. For part G, it says state the intervals where the derivative would be increasing, would be greater than 0. Well, notice you're looking for where the slope is increasing. So notice it's increasing from negative infinity to B. And then you look at the graph some more. It's also increasing from G to H. And then it's also increasing from N to O. And then for part H, it wants to know where the derivative would be negative. Well, that's where the function is decreasing. And it's decreasing from B to C, C to E, H to N, and O to infinity. And then finally, it wants to know where it's 0, where it's constant. And it's constant in 2 places, on the interval from E to F, and the interval from F to G. That's where it's constant. So here we have to end with some examples. I'll do the first one, and then I'll give you a chance to do the rest, and then I'll just post the answers. So for part A, it says, state where the values of the function is potentially not differentiable. Well, here, it's going to be potentially at 2, because that's the turning point for the absolute value. So for part B, you want to then determine if the function is differentiable or not. So what we need to do is define the piecewise function. So it's going to be x minus 2 if x is greater than or equal to 2, and it's negative x plus 2 if x is less than 2, but then remember you have to subtract 3. So it's really going to be x minus 5 if x is greater than or equal to 2, and negative x minus 1 if x is less than 2. So when you take the derivative, notice the derivative is going to be 1, and it's going to be -1 because that's the slope, at greater than 2 and it's less than 2. So that means that since f prime of 2 from the left does not equal f prime of 2 from the right, that f is not differentiable at x equals 2. So then for part C, where is f continuous? Well, f is continuous here the whole time, but however f is differentiable on the intervals of -infinity to 2 and from 2 to infinity. All right, so go ahead and try the rest on your own, and then I will post the answers. All right, first one, potentially it's not differentiable at 2 because that's a changing point for the piecewise. And it's not differentiable at x equals 2 because notice it's not defined at g of 2, so therefore it's not continuous, which means it's not differentiable. So therefore it's continuous and differentiable on that interval from -infinity to 2 and 2 to infinity. All right, the next one, so notice once again the changing point is 2. So then h of 2 is 2 when I put it in. When you find the limit as h approaches 2 from the left and right, you get that it's 2. So therefore h is continuous at 2. So it's continuous basically on the interval from -infinity to infinity. And when you find the derivative, well, this derivative from the left is 1/2 because that's the slope. From the right, you find the derivative of 2x at 2, and you also get 1/2 by doing the alternative form. So therefore, it is differentiable at 2, so it's differentiable and continuous from -infinity to infinity. For the next one, for the cube root, the turning point would be 2, so that's potentially where it's not differentiable. J of 2 is 0. When you find the limit, which means it's continuous at 2, so it means it's continuous everywhere. However, when you find the limit to find the derivative at 2, notice it's the cube root of x minus 2 minus 0 over x minus 2. When you do the algebra here, you get 1 over x minus 2 to the 2/3, and that means it's 1 over 0, which is undefined. So that means it's not differentiable at 2, which means that it's continuous everywhere, but it's not differentiable at 2. And number 8, notice the variable is x, but then the variable there is t. So that means this is a constant, which means it's going to be continuous and differentiable on the whole thing.